Good morning. I hope that all are doing well and safe. Today we are going to continue with vectors and equation of line. We're going to learn today about vector, parametric equation, and symmetric equation of a line in 3D. 3D means we are going to have coordinate system that has x, y, and z. As I said before, x, y, and z. So we are going to learn about the equation of a line in 3 dimensions. So the line is in 3D. It is not into the board. However, when I draw it, it will look like it is in the board, but it is in 3 dimensions. So as we said the last time, in order to find when we learn in 2D, we need a point on a line and direction vector. So let's say we have a point on a line and direction vector. So this is like we have a point somewhere here and we have a direction vector that's coming out like this. Okay, this is not in here, it is in the air like that. So this is the direction vector. And so the direction vector is m, and the point is, let's say, any point, and we give it x sub 0, y sub 0, z sub 0. And a vector that connects the origin with the point we know, we call it r sub 0. And as we did last time, we are going to add these two vectors to get points. So I will draw a vector that's parallel to m. And then I connect the tail of the first with the head of the last. And this will be vector r that connects any point on the line with the origin. And vector r will equal r sub 0 plus m. And as I told you, if we keep going this way or that way, we change the number in front of m, we make it 2, 3, we continue getting points on the line. So in general, the vector equation of the line is r sub 0 plus t, where t is any parameter, any number, any real number, and times the direction vector m. Okay, so this is the vector equation of a line. And we learned about, so r sub 0 connects any point on the line with the origin. R sub 0 connects the point we know with the origin. R connects any point on the line with the origin. M is the direction vector that shows us the direction that the line will be parallel to. And this is the vector equation. So let's say we have direction vector m is a, b, and c, and r sub 0 is x sub 0, y sub 0, z sub 0, and we can write this as x, y, and z because it has any coordinates, x sub 0, y sub 0, z sub 0, plus t times a, b, and c. We can separate those and write it in parametric form. So x will equal x sub 0 plus t a, y equal y sub 0 plus tb, z equal z sub 0 plus tc, exactly like what we did when we had 2D, except for we added the z coordinate. Now there is a new type of equation. It's called symmetric equation. Now if we want to solve for t in the 3 equations, we'll find that t here equal x minus x sub 0 over a, and t here equal x minus y sub 0 over b, and t here equal x minus z sub 0 over c. Okay, and a, b, and c because if they are 0, I cannot divide by a 0. I will show you what will happen if one of these are zeros. So now look, all of those are t. So those has to be equal each other. X minus x sub 0 over a equal y minus y sub 0 over b equal z minus z sub 0 over c. And this is what we call it. So this is the parametric form, and this is the symmetric equation of the line. X sub 0, y sub 0, z sub 0 are the coordinates of the point. A, B, C are the coordinates of the direction vectors. Okay? This is the three forms: vector, parametric, symmetric equation of any line. So, let us say I have let's say I have and write the equation, the symmetric equation of a line that passes through point 3, 4, and 5 with direction vector equal 5, negative 2, and 0, something like this. When we write this, it's x minus x sub 0. This is the point, and this is over a equal y minus y sub 0 over b equal z minus z sub 0 over c. Now I will put what I know. So x minus 3 over 5 equal y minus 4 over 2 equal z minus 5 over 0. I cannot do that. So how I do this? I write that z will always be 5 in this case. I will explain why. When I have a direction vector that has z component equal 0, that means the direction vector is in the floor, in the xy plane, right? So the line will be parallel to this. So it will be parallel to the plane. So all the points we have on the line will have the same z coordinate because it is parallel to the plane. So imagine that we have to the floor. So imagine this line. It has the direction vector is on the floor because it doesn't have a z component. So the line is parallel to the floor. All the points here has z component that's equal 5, which is the coordinates of the point. Okay. So if we are missing anything, so let's say if we have the same thing and we are missing m equals 0, 2, and 5. Okay, and the points 3, 4, 5 as well. I'm gonna write the same thing. So I will leave the x till the end because I cannot divide by 0. So I will write y minus 4 over 2 and z minus 5. This is another thing. This is example 2. Z minus 5 over 5, which is what I have here, and x always equal 3. And this will be parallel to the y-z plane. Okay, when when we have a direction vector that has no x component, it is parallel to the y-z plane. It is so the line will be parallel to the y. Sorry, this is x and this is y. The vector will be here, so the line will be parallel to this plane. All the x's in this will be the same. Okay. All right. So this is how we find components is 0. Okay. Okay. The next example says line 1 R equal -1, 0, and 4, and the other one S equal S that, and line 2 are 2 equal 4, -10 and -21 plus M, -2, 4, and 10. We need to know what is the relationship between these two lines. The first thing, when we want to determine what is the relationship between these two lines, we look at these two direction vectors. We will find that both of them are a scalar multiple, like M2 equals 2 times M1. So either these two are parallel or they are the same line. How we determine if they are the same line or parallel? We take the components of one of the points and put it in the equation of the other and see if we get the same S. So for example, I can take this and put it here and solve for M, or I take this and put it here and solve for S. So I will write the parametric equation if I use this point as in this line. So it will be 4 equal -1 minus S, -10 equal 2S, and -21 will equal 4 plus 5S. So in this case, from this equation, S equal 5. From this 5 or -5? -5. And S equal -5. And in here, S would equal -5. So there is a one parameter that produce this point. That means this point lies on this line. So we have this case, coincident lines. Okay, so this is one of the this is how we prove, how we show that these two lines are either parallel or the same line. We see the direction vector. If they are scalar multiple, we have these two cases. We check one point in the equation of the other. If we get the same parameter in all the three equations, that means those are coincident lines. Okay, I will stop here, and I will give you homework, and I will wait for your questions to answer them tomorrow. All right. I want to tell you there is no scalar equation of lines in 3D. Instead, we have the symmetric equation. So there is no scalar equation like what we did in the 2D. In 3D, there is no scalar equation.